So this is going to be areas, arc length, and surface area. So let's first start off by looking at the area formula for polar curves. So if I have a polar curve that maybe looks like this, then basically what it's saying is that the area is equal to the integral from a to b of 1/2 r squared dr. Oh, that's wrong. D theta. That would be very, very wrong. Okay, d theta. Okay, so now what you might be wondering is, where did this formula come from? Okay, well, this formula basically comes from the fact that you're looking for the area of a sector from trig. So if you remember, the area of a sector is equal to 1/2 r squared theta. So basically what a sector is, if you have this circle and you have this region of radius r, okay, and this whole angle is theta, okay, or basically, sorry, this angle right here is theta, then you can kind of figure out what this area is by just having 1/2 r squared and then the angle that this makes. Okay, so what you're gonna do is we're kind of going to tap into this part. So what I'm gonna have is the following. So let a polar curve be defined by r equals f of theta, and by the rays theta equals a and theta equals b. Okay, so let's say we had something that looked like that. So if I have this graph, so let's say this is my area, so let's say this is this polar curve, okay, so it can be anything, okay, and basically you want to find the area from one angle. So let's say this is angle theta, so this is theta equals a, and here we have theta equals b, and what you want to find all of this area that we have here, all of this area. That's the area that we want to find. So one way that we can do it is by taking one little slice, kind of like how we did with Riemann's sums. Okay, taking one little slice of size delta x from, oh, maybe not delta x, delta theta, because we're talking about angles. Okay, so this is the angle here, angle A, and here is angle B. Okay, and we're basically doing it from theta 1 all the way to theta 2. So the difference between theta 1 and theta 2 will give you delta theta. Okay, so we're going to do it for some sort of arbitrary theta. So we're going to have the delta theta equals theta I minus theta I minus 1. So that means that the change in the area is going to be the area of the sector, 1/2. Let's just say r in this case. We have ri star, okay? So that is just the radius of this particular sector. And then you're going to have, and this whole thing is squared, delta theta, okay? So this is going to be equal to 1/2. We know that we can rewrite r as f of theta, I star squared delta theta. So then if you wanted to take all of the area, so this is total area, well, what we're going to do is we're going to take the sum from I goes from 1 to n of 1/2 f of theta I whole quantity squared delta theta. And now, well, all we got to do is take the n as n goes to infinity. So we have infinitely many rectangles. So what we're going to have is that our area is going to be the integral from a to b of 1/2. This f of theta is just basically r squared, and then this converts to d theta. So that's basically where this formula is coming from. Okay. Similarly, you can kind of see that this can be derived by two different functions. So let's say you have the first r1 and then my other r2, and let's say you want to find the area bounded by these two different curves between theta 1 and theta 2, and you want to find this area. Okay, well, that's just going to be easy. The area is just going to be equal to the integral from a to b of 1/2 the r outer squared minus the r inner squared, okay, d theta. Okay, so this is basically if you want to find the area bounded by two different curves like this. Okay, so that's how you would do it. The outer one, this is the outer one because that's coming out outside, and this is your inner one. One way that I like to think about it is that I like to draw an arrow from the middle. So if I draw an arrow like this, the one that hits last is going to be the outer. The one that hits first is going to be your inner. Okay. Be very careful though, because there are going to be times where you want to find some other area, maybe the area on the inside. If you want to find the area on the inside, this formula is not going to work. You have to do something else. And in that case, actually the area would be just taking it from this guy. Okay. All right. So now let's do a couple of examples. Okay. So let's start off with this problem. So let's say we want to find the area enclosed by one petal of the rose curve. And here's the rose curve. The rose curve is going to be r equals cosine of 2 theta. Okay, so you want to find the area enclosed by one petal of the rose curve. Now, there's two ways that you can kind of do this. One of the ways is by drawing it out. And I'm not going to go ahead and draw it here because I have a video on that. Basically, the rose curve looks something like this. Okay, now obviously I cannot draw. Okay, so this is basically the rose curve. Okay, imagine that those are four same equal length petals. Okay, all right, so this is the rose curve. Okay, so one way that you can do it is graphing this guy, okay, and knowing what the rose curve looks like, and we want to find the area of one particular petal, so this petal. Okay, we only want one of them. Now, one of the things that you can do, let's say you don't know what this is. Well, another way that you can do it is basically where exactly are my petals located at? And usually every petal will be wherever this rose curve goes to the pole. So you can see that there's going to be some angles in which this goes to the pole. Okay, so when r is equal to 0. So when r is equal to 0, you're going to have one petal in between these angles. So one way to do it is to take cosine of 2 theta and set it equal to 0. Okay, I'm going to take inverse cosine, so 2 theta is going to be equal to pi over 2, 3 pi over 2, and then we can continue on. Usually you might want to have a couple of them. Then I'm going to divide by 2. Continue, so theta equals pi over 4 and 3 pi over 4. So basically, this theta is equal to pi over 4. Okay, this guy is going to be 3 pi over 4. Now, usually this might be a little hard because, I mean, you could do it from pi over 4 all the way to 3 pi over 4, but we can always use symmetry because you can always find the area of one petal. Now, taking two different theta values, that might be a little difficult when we do the integral. I would say start off from 0, okay, or start off from this guy. This guy right here is negative pi over 4. Okay, so do it from negative pi over 4 to pi over 4, and you'll see what happens. So you have the integral, so the area is going to be equal to the integral from a to b, okay, a to b, 1/2 r squared d theta. So the integral is going to be from negative pi over 4 all the way to pi over 4. You have 1/2, r in this case is going to be equal to cosine 2 theta squared d theta, okay? I can take out the 1/2 out. You have the integral from negative pi over 4 to pi over 4 of cosine squared 2 theta, d theta. Now, one thing that I will actually do is because if you look at symmetry, you can see that I can actually do it from 0 to pi over 4, because that's going to happen is you're going to get this top layer, and then if I just multiply this by 2, you just get the bottom part. So that's what I'm going to do. I'm going to do the integral from 0 to pi over 4. You have this 1/2 on the outside, and I'm going to multiply this by 2. And then I'm going to have cosine squared of 2 theta d theta. Okay, so this is going to go away. So you're just going to have the integral from 0. Oh, that should be pi over 4. 0 to pi over 4, and then you're going to have cosine squared 2 theta d theta. Okay, now this is an integral that we know how to do from the very beginning. All we had to do is just use the half angle formula. So this is going to be the integral from 0 to pi over 4 of 1/2 1 plus cosine of 4 theta d theta. Okay, so I'm going to take out the 1/2. The integral of 1 is going to be theta. This is going to be the integral of cosine is sine. And then you leave the 4 theta by itself and you multiply it by 1/4. And this is going to be from 0 to pi over 4. We know that the 0 is just going to go away, so all we got to do is plug in the pi over 4. Plus 1/4 sine of 4 times pi over 4. Okay, this guy is going to go away, so all you're just left with is pi over h. Okay, so the area of this one petal is going to be equal to pi over h. Okay, so there's many different ways that you can do many of these different problems, but that's basically how you would do it. So let's do another problem. Okay, so set up the integral for the area bounded by one petal. Okay, so here we have r is equal to 8 sine of 7 theta. Okay, so in this case, notice that this is going to give me a whole bunch of different petals. Okay, so it's going to be really difficult to draw. So sometimes drawing it might not be really helpful. So instead what we want to do is figure out where exactly each petal is at. So let's set this equal to 0. So when I divide 8 by 0, you're going to get 0 is equal to sine of 7 theta. So you're going to take inverse sine. So 7 theta is going to be equal to 0, pi, 2 pi, so on and so forth. Okay. Then I'm going to divide by 7. So you're going to get 0, pi over 7, 2 pi over 7, and so on and so forth. And all we just need is one petal, and we're only setting up the integral. So the area is going to be equal to the integral from 0 to pi over 7. Because that's going to be where one petal is going to be located at, 1/2. And then you're just going to take h sine of 7 theta, and then we're going to square this d theta. And since we just want to set up the integral, this would just be the answer. Okay. Now let's try this one. So find the area bounded by r equals 1 plus cosine theta, which is basically a cardioid. Okay. Now, one thing that you can do with this one's really easy to draw. So remember that this is just going to be basically a heart shaped attached at the positive x-axis. So it kind of looks like this. Okay. So it looks kind of like that, and it's symmetrical. So we would kind of take advantage of the fact that this area is going to be equal to the other area. So we want to find all the area. Okay, so because we're finding the area bounded by the entire thing. Notice that when we start drawing this, it starts at theta equals 0, goes all the way around, all the way to theta equals 2 pi. Okay, but I think it would be easier to just take one piece of the area from 0 to pi. Okay, so let's first start off by taking area is equal to integral from, it will be from 0 to 2 pi, 1/2 of 1 plus cosine of theta squared d theta. Now, since we want to take half of it, so let's just say that we want to take just this half. Okay. And then, so what we're going to do is we're going to have integral from 0 to pi. We have a 1/2 there, and let's multiply this by 2 because it'll be twice of this area. 1 plus cosine of theta squared d theta. So then see how this is going to go away. So you're left with the integral from 0 to pi of this guy. Let me FOIL this out. It'll be 1 plus 2 cosine theta plus cosine squared theta d theta. That this guy now is going to be the half angle formula. So it's going to be the integral from 0 to pi of 1 plus 2 cosine theta. So using the half angle formula, you're going to get 1/2 1 plus cosine 2 theta d theta. Okay, and now let me distribute that out. So you'll have the integral from 0 to pi of 1 plus 2 cosine theta plus 1/2 plus 1/2 cosine of 2 theta d theta. This guy and this guy is just going to give me 3/2. Then you have a 2 cosine theta plus 1/2 cosine of 2 theta d theta. And then finally, all we had to do is just take the antiderivative. So you'll have 3/2 theta plus 2 sine theta. What is this? Plus 1/4 cosine. No, that's going to be sine of 2 theta. And it's between 0 to pi. So you're going to have 3/2 pi plus 2 sine of pi plus 1/4 sine of 2 pi minus 0. And then all we're just going to be left with is 3/2 pi. Okay, so the whole area of this entire card here, this heart shape, is going to be 3 pi over 2.